Hi everyone, I'm George. I've been an intern since January on the AI engineering team doing applied ML. And I'm with Wen as well, and we're going to present our work on benchmarking and model selection for causal inference. So to start, let's think about the problem that we're trying to solve. So let's say we want to choose a treatment for a disease, and we want to answer the question, how do we choose the treatment that causes the most people to be cured, rather than just the treatment that's correlated with the best outcome? So in order to better understand what question we're trying to solve, let's look at an example. So let's look at this example here on kidney stones. So from this example, we see that it looks like treatment A is an excellent treatment for small kidney stones, and treatment A is not as good of a treatment for large kidney stones, but it's still effective. And let's look at, for example, a different treatment. Let's say treatment B. We can see that it's also better at treating treating small kidney stones, but worse at treating larger kidney stones. But we see in both cases that it's worse than treatment A. But if we look on aggregate at both cases of small and large kidney stones, we can see that treatment B performs better, although we saw that treatment A seemed to be the one that was better performing earlier. So this leads to what's called Simpson's paradox, and it's when treatment A looks to be more successful when you split it into subgroups, but when you look overall, treatment B is the one that's better. So one thing to note is that from this information is that most people with large kidney stones were given treatment A, and most people with small kidney stones were given treatment B. So what problem we're trying to solve is how can we actually measure which treatment is actually better? How can we solve that problem? So in order to solve that, we need to look at causality. So in this case, as you can see in the causal graph, as we've determined earlier, the stone size can affect both the decision of what treatment to give the patient and also the outcome of the treatment. It has an effect on both. So it's important to take that into account when we're trying to determine the actual effect of a treatment. So the amount of association and causation can be different, and this is part of the problem that we are trying to solve. So I'm going to pass it on to Wen to talk about the causal effects.
Sure. So with the causal graph in mind, we have a natural question is what is causal effect and how do we measure the effects, right? And the causal effect is actually the difference between the outcome when the treatment was applied and the outcome when the treatment was not. If we look at the graph, we have like a unit or a patient. It can be applied with treatment A and get outcome A, and we can she can get no treatment and get outcome B, and the treatment effect is actually the difference between those outcomes, which is outcome A minus outcome B. And in this case, it is also called individual treatment effect because here we only calculate the difference for just one unit. And we have another level of causal effects is that for each of the unit, we can have outcome A and outcome B and do the difference. And we can aggregate all of these results to calculate the average treatment effect. Yes. But you may have noticed that there is a fundamental problem of this kind of causal inference because the true treatment effect is the difference between outcome A minus outcome B, but we cannot observe both of them in observational data. So for details is that if an individual gets treatment A, we can observe outcome A, but we can never observe outcome B, right? And if that individual gets no treatment, what we observe is outcome B, but not outcome A. So the fundamental question is that we never observe both outcomes in the actual real-world observational data. And how can we deal with this issue is that we can actually use machine learning models to model the conditional outcome. For example, here is that we have covariates, which basically in learning setting is just features. And also the treatment is, in our case, is a binary treatment, which is whether the unit is treated or not. And with this as the input of the model, we can determine outcome y, which is actually the expected value of y given those covariates and treatment. Yes, and based on this framework in mind, we look through previous literatures and built our own pipeline for learning and evaluating those estimators. We have decided to use some popular data sets in those domains, including IHDP jobs and twins. They contain both the healthcare problems and also economic problems. And we have also implemented many estimators. For example, S-learner, T-learner, these are basically basic ML models, and TARNet, DragonNet, which we leverage the deep learning using some complicated neural network for estimation, and also some causal inference specific techniques like double robust learner and double machine learning learner. These are all the popular methods in this field. Also, we use multiple metrics like mean absolute error, that is for the average treatment effect, and PEHE, which is for the individual treatment effects. And yeah, we have put this make it a GitHub repo, but as it will be used for the Causal Inference bootcamp, so it is not open source yet, but we plan to open source it whenever we feel it is ready. Next, I will show some snippets about our work. So here, the first figure is the README page of our GitHub repo. And the second image is some popular neural network architectures, which are the state-of-the-art method for this kind of problems. And we also re-implemented it in our repo. And the third figure is some results from our benchmarks. And then I will switch the stage back to George to talk about our current ongoing work.
Yeah, so now that we have a lot of estimators that we're using to try to determine the treatment effect, we want to find a way to compare them and pick the best one. So we can use something that Wen mentioned earlier, so PEHE, which is precision of heterogeneous effects measure. And this requires that we have both our estimator's average treatment effect and a ground truth value for the treatment effect. And if we use observational data, we cannot get this ground truth treatment effect, as Wen explained earlier, as part of the problem, because we only observe one of the treatments, but not the other. So we need a solution to be able to estimate what this ground truth value would be. So using our training data, we trained our own estimators that Wen described, and we also trained other models to predict the hypothetical counterfactuals. Then, in order to evaluate our estimators, we used a validation set to calculate the average treatment effect using our estimators. And we used the hypothetical counterfactual models to determine what the estimated ground truth is, and plug these values into the PEHE calculation to try to get a value and a metric that estimates how good our estimators are. And we could use these to compare the estimators and to determine which ones are better. So what's next is that we want to apply our work to an observational data set and use the HC models that I mentioned earlier in order to evaluate our estimators on actual observational data. And we're also preparing for our causal estimate lab later on in May. So thank you everyone for listening. And does anyone have any questions?
Thank you for your presentation. So I'm fairly new to causal inference, and I'm still trying to understand the nature of the data sets that you were working on. So especially when you guys talk about hypothetical and counterfactuals, I'm just wondering, how does the data set should look like in terms of the ground truth, so that you can make your your inference, right? So I don't know if you have anything that can give us a better idea of how that data set should look like. Thank you.
Yeah, so some of the data sets that we used, some of the data sets that we used earlier already had some sort of like something we could use for the ground truth. So if we use like randomized control trials, or if we use something like the twins data set, what you'd find from the twins data set, for example, is that the counterfactuals are the same for both treatments in this case. So in the twins data set, I believe the treatment is the outcome is mortality. So you'd find for both outcomes, because they're twins, all the counterfactual data is the same. So we kind of have like a ground truth estimate already for those kind of data. But the problem arises when we're dealing more with when we don't have control trials and we don't have data that already has like data for both outcomes. So actual ground truth data where someone received a treatment, but another person who didn't receive a treatment isn't like exactly the same person. It's they have different counterfactuals. So that's why we're working on this these methods to estimate the ground truth in order for us to get to be able to get an estimate of that, since there is no actual data for two people that have the same counterfactuals but different treatments.
Awesome. Thank you. Thank you for answering. Just a follow-up question. How hard it is to get that data? I mean, how much data do we have for that, and how much potential do we see in that? Because yeah, I'm just wondering, like, I guess in order to collect that data, it's not going to be that easy, or even if it's open source as opposed to something that is being owned by an organization. I don't know if you have any thoughts about it.
Yeah, so the data that we have, yeah, like it is limited what data is available that already has the ground truth data that we can estimate. So things like IHDP or the jobs or the twins data set that we use. So it's limited number of data sets that are actually available with that. So that's why we need a way, like, because it's so hard to find that data, there needs to be a way to estimate the ground truth without having that data. And that was like the point of what we were trying to study. Like with the ground truth estimators. So yeah, it is pretty difficult to get the data. That's why we need to find other ways to estimate it without having that data.
Thank you.
Hi, this is Kenny. May I have a question?
Yeah.
Yes. Thank you for the presentation. I think this is a wonderful technique for a lot of observational study. But I would just like to understand if this kind of deep learning method, is there any advantage over some kind of more traditional statistical techniques, say the propensity score matching or weighting?
Wen, do you wanna? I think you might have more insight on this.
Yeah. So can you go back to the page that we show the architecture? Yeah. So I think this deep learning technique, it may be or may not outperform the traditional method. It depends on the data set. But from this architecture, we can see that it can use all the samples in the data set and first learn an embedding, and then based on the treatment, which is 0 or 1, and it push it into a different branch, and then use some like complicated loss function to make it a good estimator. But in the IHDP and some popular data set, it actually outperforms the traditional statistic methods, but this may not be held in the real observational data. Yeah. Yeah.
Thank you so much for the information. I think there's great potential in this technique. Thank you.
Yeah. Thank you.